In the exercise 4, actually this is also related with the context content of the lattice structure, function field lattice structure. Well, we are given a function field f over k, and let h denote the order of the class 0 group. Particularly, it is called class number. And recall that class 0 group is defined as the quotient group of the degree 0 divisors over the principal divisor. So there's a typo in the main statement. Apologies for this. And in this question, for given places P and Q with degree P and degree Q respectively, we want to see that H times QP minus PQ. So this is a divisor, and by the H times, what we mean is that indeed we consider the H summands of this divisor QP minus PQ. And we want to say that indeed this is a principal divisor. This is our claim. Indeed, we can solve these questions by using only the fact from group theory, because the first thing we can observe, if this denotes the H summand of the divisor QP minus PQ, first we can observe that this is a degree 0 divisor. So this is an element in the degree 0 divisor group. And if we have the order like H, just recall that for any group G of order, let's say X, we have that G to the X is equal to E for all G in G. And indeed, if we have the order as H, so H summoned should be the identity of this group, which is the principal group. And this gives us what we want to prove. Again, exercise 5 is related with the context to the function field lattices. Again, we are given a function field and we define the gonality as the minimum extension degree f over the rational function field. Recall that for the elliptic function field, we have the gonality is 2, but we might have several rational subfields with the same extension degree. But for the hyperelliptic, we have unique rational subfield, but still the gonality is again 2. Indeed, this is not a characterization, but still it gives us important information for the structure. And in these questions, we want to say that this quantity can be described in terms of the degree of a divisor. So the first statement is that we define gamma 1, which is defined as the minimum degree of a divisor whose dimension is at least 1. And here we want to see that this gamma 1, like the first statement is that, and similarly, let me complete the statement. We define gamma 2 as the minimum degree of a divisor whose dimension is at least 2. So we consider these subindexes regarding the dimension. And in this question, our claim is that first we want to see gamma 1 is 0 and gamma 2 is equal to gamma. And indeed, by using these two information, we can conclude that gamma is always positive, but by the definition of the gamma, by the gonality, we can also see that. So let me first show this claim. So here we only consider this definition. And to be able to see that indeed it's enough to consider the zero divisor first. Let's say I, let's say I, and for the solution of I, consider the zero divisor. And then if this is the case, we know that it has dimension 1. And by the definition of the gamma 1, if this is the minimum degree, then we can conclude that gamma 1 should be bigger than or equal to 0. And now, towards the contradiction, suppose that gamma 1 is strictly negative. But if gamma 1 is strictly negative, by the definition of gamma 1, we can see that degree should be strictly negative. But for the negative degree divisors, we know that the dimension is 0, so this cannot be possible. And we can conclude that gamma 1 is exactly 0. For the second claim, we want to see that gamma is exactly gamma 2. And for the definition of the gamma, let me consider a transcendental, which gives us exactly the extension degree as the gonality. And we know that this extension degree is exactly, it's the degree of its pole divisor. And here what we will show that like gamma 2 is less than or equal to gamma 2 first, and then secondly we will see that gonality is less than or equal to gamma 2, and we will be done. And by this choice, let me consider a divisor as the pole divisor of Z, and we can observe that its dimension is at least 2, because by the definition of the Riemann-Roch space, 1 and Z should be in its Riemann-Roch space. And by the definition of the gamma 2, we can say that the Z infinity should be in this set of divisors, and its degree is the gonality by the choice. Then gamma 2 is less than or equal to this degree, and we can first this inequality. And for the other inequality, let me consider divisor A, whose dimension is at least 2. If its dimension is at least 2, we can easily observe that it contains K, like this is a vector space over K, so it should contain K properly. So that means actually there exists, maybe instead of telling this, let me say, because I mean for the one-dimensional vector space, there might be some one-dimensional Riemann-Roch spaces which doesn't contain K. So this is why let me take my claim back. But if it has dimension at least 2, we know that it should contain at least one transcendental. So this is why we can consider such a transcendental Z in the Riemann-Roch space of F. And by the definition of the Riemann-Roch space, we know that its zero divisor minus pole divisor plus A should be positive. So here we need to argue carefully, because if the dimension of the Riemann-Roch space of A is positive, we know that degree A should be positive, right? Otherwise, like for the degree negative divisors, we know that it's Riemann space is trivial. And indeed, this gives us control. And again, when you look at this statement, degree of this statement should be also positive. So the degree of Z infinity should be controlled by the degree of A. And then, indeed, if this is the case, gamma should be less than or equal to gamma 2. And by using these two inequalities, we can conclude the equality. And for the last statement, we are given an elliptic function field. And we fix a rational place. Let me denote it by O, because we can consider such a choice by the definition of the elliptic function field. And for every rational place, we want to see the existence of a function such that the Riemann space P plus O is exactly the sum of K plus KZ. Indeed, it's enough to make an observation that for this fixed rational place, we have dimension of the Riemann spaces, this P plus O is exactly 2, because its degree is sufficiently large, which is bigger than or equal to 2G minus 1, and the genus is 1 in this case. So its dimension is exactly its degree plus 1 minus G. That means we can consider a basis with transcendental X. So we can consider a basis for this Riemann space over K. If this is the case, indeed, we can view this vector space as a vector space sum of these two vector spaces. Here, maybe what you can observe is that indeed this vector space can be seen as the field FQ of X. And then we complete the solution.